Walk through the long-awaited solution to homework 3, problem 10. Now, this involves, shockingly, a free body diagram for the two masses involved. We have the force of the bowl on the cube as one of our first forces. We have the weight of the cube. So I always start like this. And I'm going to get a little fancy and note that this angle here is going to be theta. Doesn't matter where it sits. This is going to be a parallel line. That'll be theta. And so these two are alternate interior angles of parallel lines. We're all good. Okay, the bowl has 4 forces on it. It has a force that's being pushed on. It has its own weight. It has a normal force, which I forgot in my original video. Turns out not to be important. And it has the equal and opposite force of this contact force, which is the force of the cube on the bowl. And then this angle is theta, because these are parallel angles in the diagram here. Now, given that, I can write down Newton's second law for all the directions of the problem, the y and the x. I only need 3 of them. I need the cube. I need the sum of the forces in the x direction. Well, that's only one. It's the sine component of this force. So it's the FBC sine theta component there. And that has to be mc times the acceleration. I'm just going to use that straight up later. So I'm going to call that equation 1. We're going to come back to it. The sum of the forces in the y direction is going to be 0, because there's no acceleration up and down. So ma on that side is 0. That's where the 0 comes from. And then we write down the sum of the forces. That's f bc times cos theta minus mc times g. OK, that's good. Need this one for later, so I'll call that equation 2. Then finally, equation 3 is for the bowl. And that's the sum of the forces in the x direction. And that is equal to the mass of the bowl. Let's erase that. Don't need whatever the heck that turned out to be. Come back. Boom! Mass of the bowl. Mass of the bowl times its acceleration in the x direction. So the sum of the forces is what's providing its acceleration in the x direction. And so that's equal to the sort of motive force, whatever's pushing on it, minus FCB. And this is the sine theta component. I picked a minus sign because it's going opposite, going back in the negative x direction. And we'll need this for later. So let's call that, oh, it's already called equation 3. So everything's good. The very first thing I'm going to do is solve 3 the very first thing I'm going to do is I'm going to plug 1 into 3. And I get FBC sine theta, and here's FCB sine theta. I happen to know that because FCB is equal to FBC, we're all set. And so I can go ahead, that's Newton's third law, and then I can just plug in mc times a for this second term right here. And let's go ahead and do that. That is the mass of the bowl times the acceleration is equal to the force minus the mass of the cube times the acceleration. And from there, I can solve for this acceleration by saying mba plus mc times a is equal to the force. Factor out an a from both terms on the left-hand side. So that's a times the sum of the masses, m bowl, plus m cube. And then from there, we get that a is equal to the force over the sum of the masses. Mass bowl plus mass cubed. Mass cubed. There it is. OK. Now, this gives us an acceleration in terms of things we know. So that's great. We can get rid of that business. The next thing that I do is I used this equation 2. So solve equation 2 for FBC cos theta. So I know that 2, I'm going to start out with the mc times g equation is equal to BC cos theta. And since I know where I'm going with this problem, I've got to get that theta, what I can do is I'm trying to find an expression that allows me to figure out what theta is. And I do know something about theta. I know something about FBC sine theta is the mass of the cube times the acceleration. I already know the acceleration, so it seems like a good direction to go. So I can actually get that isolated by taking this term, cos theta, and multiplying and dividing it by sine theta. This is a trick. You can brute force this through any way you like. I thought this was sort of the most clever approach because FBC times sine theta is something I know. And just rewrite that, commute some terms in multiplication, FBC sine theta. And then this, of course, turns into cos theta over sine theta, and that's 1 over the tangent. And it looks like what we should solve for, and then FBC sine theta. This from there is from equation 2. So I'm going to plug 2 into this expression right here, and I'm going to get that this is equal to, plug 1. Let's get rid of that. 1. Plug 1 in there, and that gives me mc times the acceleration times 1 over the tangent. Now, let's look at the beginning of the expression and the end of the expression. We get, let's bring them together just so we can see what's going on. mc times g is equal to mc times a times 1 over the tangent of the angle. And this is a fairly simple expression. I can cancel out the mc and solve for tangent theta. And I get that the tangent of the angle, whatever it is equal to the acceleration over gravity. And that's something you could probably just anticipate from the setup of the problem, but we had to sort of go through the math to convince ourselves of it. Fortunately, we know what the acceleration is. That's right up there. F over the mass of the bowl plus the mass of the cube, and that's divided by 1 over g is the tangent of the angle. And from there, what I can do is I can just use the arctangent to figure out the angle. So theta is equal to tan minus 1 of this entire mess, F over mb plus mc times 1 over g. All right, and that is the solution. You can plug in your values and come to the answer that is desired. Thanks a lot for